So, we've all heard the story, right? A warmer planet means more disease. It just feels logical, almost obvious. But what if that simple story we all tell ourselves is actually dangerously incomplete? Let's really dig in and deconstruct the real connection between climate change and disease.
I mean, the idea is pretty straightforward. As the planet heats up, all those disease-carrying mosquitoes and ticks can suddenly survive further north, bringing nasty tropical illnesses right along with them. It feels like simple cause and effect. But is that really the whole picture?
According to researchers like Marieta and her team, while that simple narrative is great for grabbing headlines, it leaves out some absolutely crucial details. And for the policymakers and health experts trying to keep us safe, those missing details make all the difference. The reality is just way more complex.
And the very first layer of that complexity is realizing we're not just talking about warming. We're talking about massive, interconnected global change.
Okay, so this is the first big mental shift we need to make. We tend to get laser focused on global warming, that rising number on the thermometer. But the real game is global change. Think about it. It's not just heat, it's everything. Weird rainfall patterns, how we chop down forests for farms, the billions of tons of goods we ship across oceans, the planes we fly every single day, and the way our cities sprawl. Each one of these is a potential highway for a disease, and sometimes it's a much more direct route than a 1-degree temperature change.
And the researchers, they put it pretty bluntly. They say focusing only on climate is straight up misleading. It makes us ignore this whole web of other factors. Now, don't get me wrong, temperature matters a lot. But it's just one piece of a very, very complicated puzzle. All this complexity? Well, it makes predicting the future incredibly difficult. Scientists use models to try and see what's coming, but as we're about to see, these models have some really serious limitations.
So how do scientists even try to predict this stuff? Well, they've got two main tools in their toolbox. On one hand, you have what are called mechanistic models. These try to build a little biological world inside a computer, often using data from a lab, like how does heat affect a mosquito's breeding cycle. Then, on the other hand, you have statistical models. These guys are more like pattern finders. They'll notice that, hey, whenever rainfall goes up in this region, cases of a disease follow. They don't always know the why, but they spot the what. Both are powerful, but both can miss the forest for the trees.
And here is the huge, flashing warning sign. A model is only as good as the assumptions you bake into it. A mosquito living its best life in a clean, perfectly controlled lab is just not the same as a mosquito trying to survive in a polluted, chaotic city drain pipe. The real world is messy. So we have to be super, super careful not to treat a model's prediction like it's a message from a crystal ball.
And that leads us to another really common trap. It's one thing to look backwards, at data from the past, and connect the dots to explain why an outbreak happened. It's a whole other ballgame to try and use those same dots to predict what's going to happen next.
Exactly. The past just isn't a perfect blueprint. Just because two things happened at the same time before doesn't guarantee one caused the other, and it certainly doesn't mean the same thing will happen next time. Especially when you're talking about those really rare, high-impact events. By their very nature, they're almost impossible to see coming.
Okay, so if the simple story isn't right and prediction is full of holes, what are public health officials supposed to do? Just throw their hands up? Well, no. The researchers don't just point out the problems, they actually propose a really practical way forward.
They argue for something called a contextual approach. Basically, instead of trying to make these huge, sweeping predictions for the entire globe, we should zoom in. We need to focus on understanding the specific risks and the on-the-ground reality of a single region, or even a single city.
And this table, this is where their big idea really clicks. They break down the threat level into 5 different contexts based on 3 simple questions. 1, are people actually getting sick here? 2, is the virus or bacteria itself present in the environment? And 3, is the right kind of mosquito or tick here to spread it? Okay, let's use their example of Western Europe. For a disease like Japanese encephalitis, the answer to all 3 questions is no, so that's a context 5 risk, super low. But for West Nile virus, the mosquito that carries it is there, even if the virus isn't common. That puts it in context 3. Right away, you can see how your public health plan for those 2 threats would be completely different.
This whole framework boils down to a clear, 3-step plan. First, figure out your local context. Where do you fit on that table? Second, you target your surveillance based on that context. Are you looking for a new type of mosquito arriving at the port, or are you testing the mosquitoes you already have? And finally, you can act effectively because your plan is perfectly tailored to the real specific risk you're facing, not some vague global fear.
So, to see why this context is king idea is so powerful, let's look at a real-world example. The story of the first ever outbreak of chikungunya virus in Europe. Back in 2007, a part of Italy had a local outbreak of chikungunya. Now, the easy answer would be to just blame climate change. But when you look closer, the reality was a perfect storm of three very specific events. First, the virus itself mutated in a way that let the Asian tiger mosquito carry it, a mosquito that was already well established in Italy. Second, one single person infected with this new strain got on a plane in India and landed in Italy. That was the spark. And third, that spark landed in the perfect kindling, a dense local population of those exact mosquitoes, who then spread it to more than 200 people.
So you see what happened. This wasn't caused by a slow, gradual rise in temperature. It was a bizarre coincidence of a biological mutation, modern air travel, and a local bug population. It was 100% about context. All the wrong puzzle pieces just happened to snap into place at the exact same time.
And this brings us right back to the role of climate change. It's a huge factor, a powerful one, but it's just that, one factor. It sets the stage, right? It influences the background conditions. But as we just saw in Italy, it doesn't write the whole script. It does not, by itself, determine where and when the next outbreak is going to pop up.
All of this brings us to the final and I think most important takeaway. We started with what seemed like a simple question, but the science is telling us we need to be asking a much smarter, much more practical question instead.
Instead of asking this big, abstract question, is climate change a threat? The most powerful thing we can do is ask a local one. What makes my town, my city, my community vulnerability? Is it that we have a certain type of mosquito? Is it that our airport is a major hub for international travel? Do we not have good systems for tracking diseases? Because once we understand our own unique context, that's when we can finally move from general anxiety to effective targeted action. And that is how we really get ready for whatever the future holds.